It is still in the.
No,
it's open.
It's perfect.
Yeah. Okay. Okay. Thank you. Thank you. So this one talks about like the same MFPs2 kind of results, but on the Slingshot system. As many of you know, the Slingshot is the new Interconnect kind of things. So I'll try to provide the presentation as follows, starting with a very brief introduction and the MPI plus Slingshot. And we'll try to show some CPU level performance and then GPU level performance, and then I'll conclude. But before I go into this, I'll just try to indicate some caveats here. I mean, so these results have been taken from Oak Ridge National Lab, the SPOCK system. Those who are familiar, this is the first generation, like the results will be on the Slingshot 10, and the Slingshot 11 is being deployed. And Oak Ridge has, I mean, these machines are very small in the beginning, so there is a very restrictions on how many nodes you can access. And also for all the results, you have to get an approval. So I'm just trying to indicate. So here we have got all those approvals. So these are the very first set of initial numbers I'll try to be showing. But then as we get access to larger number of nodes, and then the Slingshot 11 will be very, again, in the future, we'll be happy to show the performance numbers. So at a high level, as you know, the HP Cray Slingshot has been in the discussion for many years. And these are especially becoming very important as especially the Frontier at the Oak Ridge National Lab and the El Capitan at Livermore will be used. And of course, the Slingshot is also being planned for Aurora by Intel. And especially here, the results are from the OLCF. And Slingshot has a lot of features like adaptive routing, congestion control, QoS features. Of course, we will not be showing any results with respect to those. So this is the system on which we have taken the numbers. This is the SPOCK compute node. So this is by the way, the Slingshot 10. I'll just try to clarify first. So these are the AMD nodes with like a 64 cores here. And we have the AMD GPUs here. These are the MI100 GPUs. And they are being connected here, as you can see, with the Infinity Fabric. And here we have the PCI Gen 4. And this is the NIC, which is the Slingshot 10 is connected here. Okay. And I'll just skip this. I introduced this MFPs2 project earlier. I'll skip this. So what we try to do, just to see what is the state of the art. Again, this is not telling, I don't want to say this MPI library is the best or something like that, because these are very initial evaluations. So we just took our MFPs2 libraries. We have a GDR version, GPU Direct RDMA, which is optimized for GPUs, both NVIDIA and AMD. We use that for the GPU-based things. And then the MFPs2X, which is optimized for CPU. So those is the library from our side. Then we took the OpenMPI 412 when we took this result, okay, during that time. And in fact, we are presenting here, and I'll try to show this. These results also has been accepted to be presented at PERC conference. With some more detailed things we'll present by the time if we get some more things. So what I'm trying to show here is like just I believe around 2 months old when we took all these numbers. And then we took the Cray MPH 8110 and then the RICL. That's the library, as you know, just like the NVIDIA nickel equivalent. AMD has the RICL. So those are the kind of the environments we did. And here the AMD has the ROCm version 5.0, AMD EPYC, and then MI100 GPUs. And we use the OSU Microbenchmarks 5.9 version. That is the latest version, which is publicly available. So all of these results you should be able to actually reproduce and replicate. So let's start with initial like a point-to-point INTRA-NODE. Okay, so that means within that AMD node, when we are trying to do latency and bandwidth and bidirectional bandwidth. And as you can see here, so this is the x-axis is the message size. This is the latency. So here, as you can see, the MFPs2X is running with the XPMEM support. And by the way, the other builds, these are the default build. Whatever is available on those systems, we are taking. Okay, Cray MPH, OpenMPI, because we don't have knowledge on those. So we have not, I mean, we have not spent a lot of time on optimizing those other stacks because we don't have knowledge. Okay, I just want to say that upfront. Okay, but I'm sure, I mean, if people come up and then optimize the stack, we can reevaluate those things. Okay, Same thing with also OpenMPI. So here, as you can see, like this is the INTRA-NODE. MFS2X has not only XPM support, it has some cooperative protocol for very large messages. So you can see we are able to get at a small range. It is like the MFS2 and OpenMPI are reasonably close. CRAMPH has some higher overhead. We don't know why. But at the message size increases, you can see that MFS2X is winning over. For very large messages, there are some issues with MFS2X. We may need to also do some tuning here. Up to 2 megabytes, we are good, but after that, we are not good. And then the bandwidth wise, here again, we see all different kinds of trends here. In the MFS2X, we are able to go like around 39 gigabytes. I mean, broadly, they are same. All the three MPI libraries are performing very similar for bandwidth and bidirectional bandwidth. So then this is the INTRA-NODE. So this is where it is going over the Slingshot 10. So here again, like we have provided two kinds of numbers. On the right-hand side, it is trying to say, let's say, MFS2 latency at 1 byte. Here we can see OpenMPI is doing the best, like a 2.28. MFS2X is next to that with 2.55 microsecond, and CRAMP is around 3.15 microsecond. And as the message sizes are going into the medium range kind of things, so we see a little bit of changes here. 4.95, 514, 524, very close. And of course, the large messages, they remain almost the same. And then the bandwidth wise, here again, short messages, we see a little bit difference, but as the message size becomes larger, all the three MPI libraries are performing very well. Bidirectional bandwidth, we see some differences. And especially in this medium message sizes we see, but very large message sizes, again, all of them are performing very similar. So then on the CPU side, the collectives, that plays a very big role, just like I introduced in the previous talk. So these are all the, by the way, the blocking collectives, not non-blocking collectives. So we have a broadcast and reduce here. So here, as I said, they have a restriction on how many number of nodes you can use. We are able to only go for 4 nodes, 64 ppm, 256 process. That's all we are trying to show the numbers here. Once we get larger scale access, we will be able to bring those results to you. And especially here, as you can see, like the small message sizes, OpenMPI is performing the best. CRAMPH and MFS2X are similar, but as the message size increases, because we have the point-to-point performance better in the MFS2X, we are able to deliver better compared to the other two stacks. And then the right-hand side, if we go even beyond much more bigger messages, here we see MFS2X is coming next, and then the CRAMPH is actually trying to do the best here. And then these are the reduced numbers, and again for small medium messages and large messages, up to small and medium, here MFS2X is performing the best compared to others. I think here you can see might be there is some tuning issues here. The CRAMPH people need to optimize this better. Similar kind of things are also happening on the right hand side. And then the other collectives, the common ones are gather and all gather. And here we see the gather, the same kind of graphs are here, around 5.23 for very large messages. MFS2X performs better, comes to 5.4. All gather, also we are able to do very good here, and also for large messages. The other common collectives are like all reduce and all to all. These are also very important. And here we clearly see like especially all reduce. MFS2X has a lot of optimization. It uses the XPM kind of mechanisms, also that cooperative protocol. And here we are able to win over compared to the other stacks for small, medium, and large messages. And with respect to all, here we see the CRAMPH is performing the best. And here and OpenMPI are very similar kind of things for very large messages. So now let's move into the GPU, because this system not only is the CPU, it has the AMD GPUs. So here again, we took our MVAPs to GDR. If some of you are not familiar, this GDR stands for GPU Direct RDMA. So we have been supporting this GPU Direct RDMA design in our MVAPs2 library for many years. We started with NVIDIA, and now actually it is incorporated also AMD support. So under the same framework, you can actually support both NVIDIA GPUs and AMD GPUs. So we have taken that version and comparing with OpenMPI and Cray MPI. So now if you see, like this is a intra-node. That means within the node, we have several MI100s. So the question is, how much time does it take to move data between these? And in addition to the GPU Direct RDMA, there are a lot of other kind of libraries get used. These are called GDR copy. These are like the PCI bar mapped memories for small message sizes. So I think all the libraries are using those kind of optimizations in addition to the GPU Direct RDMA. And also in these designs, some of you might be familiar, also there are a lot of different protocols, like when to use GPU Direct, GDR copy versus where to use GPU Direct RDMA. All the stacks need to be optimized, okay, for any given platforms. This is what we have seen over the years, based on how the GPUs are connected over the PCI bus or over NVLink or over Infinite Fabrics, because the communication performance differ. So for every such system, you need to optimize to get the best performance. Okay, so here we are seeing at very lowest level, like the minimum latency, as you can see in 1 byte, MFS to GDR, GPU to GPU. Within the node, we are able to transfer the data at 2.65 microsecond. Okay, and it's very little additional overhead compared to what we saw earlier. OpenMPI is trying to do similar kind of things in 3.78, and Cray MPI is around 3.11. So all these are more or less similar, as you can see. But as the system size, as the message size increases, we see some differences. And again, I mean, these kind of things needs optimizations. Might be the Cray MPI people need to optimize here, and OpenMPI also. I believe they're changing the protocol here from small messages to large messages. Sorry, the 64 to onward. So they may need to see if there is any other solution which is available here. So whereas if you see the MFS to X is trying to keep it very sustained, up to like a 5.46 microsecond, up to 4 kilobyte. But as the message size increases for very large messages, the Cray MPI totally wins over here. There is a big gap. And MFS to X, MFS to GDR, we are actually exploring why we are going over that much. We may need to do some additional optimizations to bring it down. The bandwidth and bidirectional bandwidth, we saw a big difference. I mean, again, as you can see the numbers, MVAPs2 and OpenMPI. So MVAPs2 is able to get around 102 gigabytes per second. OpenMPI UCX, I don't know, it is performing not so good here. Again, might be some of the OpenMPI team people can take a look at it, but Cray MPI is doing very good here. It's almost like beating all the other libraries in a big manner, with the bandwidth, and similar things we also see in the bidirectional bandwidth here. So then this is the on the GPU, but now it is the inter-node. Across the node, we are trying to do like the sending data from one MI100 to the MI100 in the other node over the Slingshot 10. So that's the thing what we are trying to show here. And as you can see, at the small messages, again, all these three libraries are very similar. In this scale, they are not coming out, but broadly they are similar here. If you see 4.28 versus 5.18, 4.76. These latencies are little bit, if you do NVIDIA comparison, we are not showing because this is taken on a one given system, but with NVIDIA platforms and all, with the latest GPU-directed RDMA, we have seen better numbers. But again, these new systems are coming up. There might be more and more optimizations, or the ROCm library is coming later on. We'll see how these get optimized further. And as the message size increases here, the latency wise, I think both OpenMPI and MVAPIS2 are more or less doing very similar. And the CRAMPs has a little bit higher overhead in a consistent manner, kind of things. And so then on the bandwidth and bidirectional bandwidth here, as you can see, as the message size increases, like a 4 meg, broadly they are performing very similar. In the lower end, there are some differences here. Again, CRAMP is not performing very well. It starts with very low, but picks up. And here effectively, as you can see, like we're getting very close to 9.5, 9.8 gigabytes per second. That is the Slingshot 10 bandwidth kind of thing. So then the question is now the GPU-based collectives, because a lot of these deep learning applications, even a lot of HPC applications are also trying to utilize GPU-based collective. So that plays a very big role in your DL training time and all. So here we try to evaluate it. So these are again 4 nodes, 4 PPN, 16 GPUs. That is the largest access we got. So here you can see, and here we compared with also the recall. Because just like the nickel from the NVIDIA libraries, AMD has the recall library. They have also been optimizing. So these the first three are the MPI driven solutions. And then, of course, the recall is their own solution. So we are trying to compare where these things sit next to each other. So here again, as you can see, like for small and medium message sizes, MVAPIS2 GDR is performing very well. Next is the OpenMPI, then CRAM pitch, but recall latency is very high. I don't know what exactly is happening there. Might be they need to also optimize. That we see consistently, at least in the broadcast, as you can see, even for the large messages. Recall still has additional overhead here. But CRAM pitch is coming up very good for very large message sizes. And reduce, which is the reduction operation. Here we see a little bit like a different trend. So for a small and medium messages, the recall is not good, but as it goes to very large messages, recall and MVAPIS2 GDR are performing very similar. And next is the CRAM pitch, and then the OpenMPI. Again, I mean, I'm just showing these numbers. As I said, these are all initial set of numbers. Each of the stack, I am sure people will keep on optimizing, including us. And then you will see as the systems get deployed, we'll see like which stack is able to deliver a lot of better performance in a uniform manner for a lot of applications. I don't know that answer yet. These are again just the preliminary numbers I'm trying to share.
Okay, we had a question on the slide.
Yeah, this slide. Okay.
On 17, sorry. Yeah.
Yeah.
So there was a bit of someone said that was it a mix-up, or someone said that GDR copy was used with the MI100 setup, or was it GDR-like alternative for ROCm?
GDR-like alternative.
Okay, thank you.
Yeah. So the same GDR, like we are trying to utilize the GDR copy in the AMD context. Yeah.
Cool. Thank you.
Yeah. So then for the other collectives, so here we evaluated gather and all gather. And here again for gather, we see like a small to large messages. Similar trend like a MVAPIS2 GDR is performing very well. The recall starts with very high, but actually performs better for large messages. And then and then here the CRAM pitch is somewhere in the middle, and OpenMPI is again does very well in the short messages and then goes up. And then for the all gather, here there's a lot of fluctuations happening, at least for recall we see here, and MVAPIS2 GDR is able to hold on for small, medium, and large messages. Even CRAM pitch is also trying to do very good for large messages. OpenMPI is shooting up here. I'm sure this also needs different algorithms, different tuning there. So then the final set here, the all reduce and all to all. already we see very similar trend to the previous one. With the MFP to GDR, we are able to perform uniformly well for small, medium, large messages. All to all is also very similar, and Recall has higher overhead on both these things, all reduce and all to all. But for very large messages, they are performing very well. And OpenMPI is starting here. All to all is things that I'm sure there's some algorithm changes are happening here. So those algorithms need to be tuned properly on these platforms. So with this, let me conclude here. As I indicated, these are the very first set of numbers in the community we have done with this new Slingshot interconnect, and we have this paper accepted to be presented at PERC 2022 in July. And between now and then, of course, based on the access we'll get and the approval process we'll get from OCRIS, we'll be able to share additional numbers at the PERC conference. So and while these are Slingshot 10, I mean the Slingshot 11 is being worked on. Those numbers have not been run completely, and we don't have approval yet. So that will also be the next stage. We'll be trying to show the Slingshot 11 how these all the different libraries are performing, so that the end users will get an idea on which library to use and to for their applications. So with this, let me conclude here. If there are any quick questions, I'll be very happy to answer.
Are there any questions from the audience? We have a minute or so. Okay, DK, thank you very much for your talks this morning. I enjoyed them very much.
Thanks a lot. Thanks.